Is my screen visible?
Not now, ma'am. But before it was like before 1 minute. Now it's visible.
Okay. Okay. All right. So let me start with the class. So at the end of the class, I will have some discussion with all the students of the class. So people who just leave right after I end the class, so you can also stay in the class. Okay. And yeah, Meenu and Shivank, I hope that you are taking the attendance during both the times.
Yes, yes,
Yeah.
ma'am.
Okay. All right. All right. So in the last class, we had talked about go back in, right? So I am not repeating it, except the fact that what we had seen in go back in was that, if there is a packet loss in between, then if the nth packet is getting lost, so the sender will send the n plus 1, I mean, starting from n plus 1, how many number of packets were sent to the receiver. So that is why it is like in a cumulative way they are sending the packets. Okay. And what was happening at the receiver side is that if any packet was received or which is out of order, that is, which is not what the receiver is actually expecting, so the receiver will receive that packet and sends an acknowledgement of the last packet that was received, and that was correct packet. That means that was received in the correct order. Okay, so that's what we had studied in case of go back N protocol. Now the problem with go back N is that we are basically wasting a lot of resources. So can we have a better protocol than this one? So with this came the protocol called as selective repeat protocol. So what's happening here? So receiver will individually acknowledge all the packets which are received correctly. Okay. So correctly received here means that packet is fine. There's no error in that packet. All right. So if a packet is correctly received, then the receiver will receive it. How will it receive? So even if it is out of order, how will it receive it? It will simply keep it in a buffer. Okay, so that once all the packets which are in sequence, they are received at the buffer, then they will be sent to the above layer, that is the application layer. Also, then you can ask me the question that what would happen that if the sender times out. Okay, so what will the sender do? The sender will of course retransmit the unacknowledged packets, but it will only send that packet which was not acknowledged, right? It will not send all the packets after that, as was being done in case of go backend. So by this way, it is reducing the amount of resource utilization that was happening in case of the go backend. Okay, so basically what the sender does is for each packet that it sends, it will have a timer. So for each unacknowledged packet, the sender is having a timer. Once the timer times out, then of course it gets to know that it has to retransmit that packet. Okay, so there's a sender window in the selective repeat protocol, which is having, as we had in go back n also, that the window is of size n. Okay, so we have n consecutive sequence numbers. Now there will be a limit to the sequence numbers of the sent packets and to the unacknowledged packets. Okay, so we'll see how the sender and receiver windows work in case of selective repeat. Okay, so this is from the sender side. Okay, so this is the send base of the window. So that means the window is of n size. Okay, so these are the packets which are in yellow and green in colors. They were sent already. The green colored ones are the ones which have been acknowledged. Okay, and the yellow colored ones are the ones which have not yet been acknowledged, but they have been sent. And the blue ones are still in the window, so they can be sent afterwards. They are not sent yet. Okay, So that means if the pointer is put here, this is the send base and this is the next sequence number that can be sent. Okay. Now, how the receiver views the sequence numbers. Okay. So from the at the receiver side also we have this same window size, but how does the receiver look at these? Okay. So the pink ones, as you can see, these are out of order packets. So basically they have been received at the receiver side, but they are out of order packets. Okay. So what we know about selective repeat, it can buffer these packets. Okay. So it will buffer these packets and it will send the corresponding acknowledgements. So those packets are here. Um, just a second. Yeah. So I hope that you can see the laser pointer here. So these pink colored packets, they are basically out of order packets. They are buffered and they are and their corresponding acknowledgements have been sent to the sender's side. Okay. All right. Now the gray ones, okay, these are the ones which are expected in sequence. Okay. So these are the packets which are expected at the receiver side, but they have not yet been received. And the blue ones are the ones which are basically acceptable within this window size, and the green ones, they are already received in order. These ones are not usable. Okay. So let's check what are the tasks that are there from both the sender side and at the receiver side in case of selective repeat. Okay. So what happens at the sender side? First things first, as we know that the data has to come from the above layer. Okay. So if the next available sequence number is in the window of the send packet. So let's check here. So if the next available sequence number is within this window size only, then the packet can be sent, right? So that's what it is happening here. So if next first the check is done, that is if next available sequence number is in the window, then send the packet. And of course we are starting a timer with sending the packet. So if there is a timeout, then what the sender will do, it will resend the packet and then it will restart the corresponding timer. Okay. Now, if an acknowledgement is received, okay, so suppose the nth packet's acknowledgement is received and this acknowledgement is between send base to send base plus n. That means if the acknowledgement is between this window, okay, so in that case, what would happen? That packet n is marked as received, okay. Now, if the nth smallest unacknowledged packet is advance, okay, so then what would happen, that you advance the window base to the next unacknowledged sequence number. Okay. So basically if you have the nth smallest unacknowledged packet, so then what you do, you advance your window base to the next unacknowledged sequence number. All right. Now, at the receiver side, something similar is going to happen, but from the receiver's point of view. So, how will we look at? So, suppose receiver's task is to only receive the packet. So, if the packet belongs to the window of the receiver, that is from receive base to receive base plus n minus 1. So, if it is in the window, so then you send an acknowledgement. Okay, acknowledgement of that particular packet. Now, if the packet is out of order, than what was expected by the receiver, so then what the receiver would do, it will simply buffer the packet. Okay, we are not discarding the packet here as was being done in go back in, right? So it will buffer the packet and it will wait for all the packets which are in sequence to come, and then it will deliver it to the above layer. Okay, but if it is received in order, then everything is good. Then it simply delivers all the packets which are in order and they are also in the buffer, and then it delivers it in the above layer. Okay. Now once the delivery is done, then it advances the window or moves the window to the next not yet received packets. So if you look at these, okay, so the gray ones are the not yet received packets. Okay, so once one of these packets is received, then the window will be slid to the next not yet received packet. Okay, so if you see these kind of protocols, so there's a terminology that is used for these kind of protocols. They are also known as the sliding window protocols. Okay, so you will see, if you read the book, you will find it out that these protocols, so essentially you are basically sliding the window, right? As and when you are at the sender side, as and when you are receiving the acknowledgement, you are sliding the window or moving the window forward for sending more packets. And in the receiver side, as and when you are receiving a packet, you are also sliding it forward. Okay, so that's why it is known as sliding window protocols. Now, n to receive base minus 1, then we definitely acknowledge this particular packet. Okay, otherwise we ignore the packet. So basically, if it belongs to the window, we acknowledge it, otherwise we simply ignore the packet. Okay, so let's see how it works out. So suppose this is a similar example as was given in go backend. Okay, so we have a window size of 4 here. Now, in the beginning, you have sent all 4 packets starting with sequence number 0. Okay, so once this is done, so now that means that the sender has started a timer. So there is a waiting going on here at the sender side. Now, this packet 0 is received at the receiver side, an acknowledgement will be sent. Packet 1 is received, again an acknowledgement will be sent. So that's how it is. Now in between, packet 3 is also sent. Okay, sorry, packet 3 is received and you send the acknowledgement 3, but you also keep it as a buffer. Now in between, packet 2 is lost. Okay, so packet 2's so basically packet 2 is not received at the receiver side. So since when packet 3 is received at the receiver side, the receiver knows that this is not what it was expecting, so it simply buffers it and sends the corresponding acknowledgement. Now look at the sender side. As and when it is receiving the packet, the acknowledgement for a particular packet, it is simply sliding the window by 1. Okay, so see, as we receive acknowledgement for packet 0, then the window is slid by 1 and packet 4 is being sent. Okay, so now you can see packet 4 is sent. Packet 4 is received also at the receiver side. So since this is also out of order, so it will buffer it, but it will send the corresponding acknowledgement. So similarly for packet 1, when acknowledgement 1 is received at the sender, again window will be slid further and packet 5 will be sent. Okay. Now this is the acknowledgement that is arrived for packet 3 at the sender side. So now the sender knows that packet 2 has not yet, so we do not have the in sequence acknowledgement also. So sender knows that there is some out of order delivery being going on because it has received an acknowledgement which is different from what it was expecting. Okay. So now once this has happened, then after that what happens is that the timeout happens for packet number 2. Okay. So now it knows that packet 2 was lost probably in between. So it again resends the packet, but it only resends packet number 2 and not packets 3, 4 and 5. Okay. Which were sent after this packet. Okay. So now look at the receiver side. So packet 2 is sent. Once the packet is received at the receiver side, now see, all the packets from 3, 4 and 5, they had been buffered because receiver was expecting packet number 2. So once packet number 2 is delivered, then all the packets from 2, 3, 4 to 5, they are all, moved up. That is, moved to the upper layer from the buffer, and corresponding acknowledgement for packet 2 is transferred to the sender side. All right. So now the question would be that what happens when packet 2 is actually arriving? Okay. So can anybody tell me what would happen if packet 2 arrives? When packet 2 will arrive, what would happen? Any answers to this question? I should know at least that, I'm just not speaking to air or something like that.
Ma'am, the window would be moved one step to the right.
Okay, but packet 4 and packet 5, if we receive the acknowledgements for packet 4 and packet 5 before the timeout of packet 2 happens, then do you think the window should be moved forward?
No, ma'am, the window should stay there.
Okay, so just do some examples on selective repeat. Okay, just see that how it should work out. So these are these are pretty important and very interesting also to see that how the window is actually going to move. All right. All right. So let's see what can be the problems in case of selective repeat, because essentially it seems that it's a very good protocol, right? It does not have many much wastage of resources as was happening in all other protocols, right? So let's see. Okay, so here we have an example where we have a window size of 3. All right, and we can have um, 4 sequence number, that is 0, 1, 2 and 3. So here packets 0, 1 and 2 are being transferred. So this is the receiver window, this is the sender window. So the receiver window is of course moving as and when it is receiving one packet. Okay, so it received packet 0, so it moved to 1, 2 and 3. When it received packet 1, it is now moving to 2, 3 and 0, and so on and so forth. Now what happens is, so at the first step everything goes well. So the acknowledgements of corresponding packet 0 and packet 1 have been received at the sender side. So once the acknowledgement for packet 0 is received, the window is moved by 1 at the sender side. Once once the acknowledgement for packet 1 is received, again the window is moved. Now this packet 3 that was transferred from the sender side, if it is lost in between, suppose, okay, so then this guy, uh, of course after receiving the sender side, of course after receiving the acknowledgement for packet 1, it will again move the window a little bit more. So again it will go to sequence number 0 and it will transfer packet number 0. Okay, now what happens in the receiver side? Okay, so the receiver side is now, whenever the packet is received, it checks that whether the packet is in the window size that is there at the receiver side. So it sees that yes, it is in the window, and it will receive the packet with this sequence number of 0. Okay, so no problem in this situation. Now let's come to the next example. So we have again the same windows, packets are being transferred, but unfortunately the acknowledgements are not getting received at the sender side. Okay, so then what would happen, that there is a timeout, and there is a retransmit of packet number 0. Now look at the case here. So what's happening? When packets are getting received at the receiver side, the receive window is sliding forward. Okay, So 012, 012, these sequence numbers have been received at the receiver side. Okay, so now the receive window is moved to this part where it is expecting packets 3, 0 and 1, these sequence numbers to be received. Okay, now look at the sender side. The timeout has happened and it is retransmitting packet number 0, but this packet is the first 0, this sequence number. It is not the second 0 packet, second packet with 0 sequence number. So it sends the first packet with 0 sequence number, but the receiver will think that it is the second packet with 0 sequence number, right? So why? Because in its window, in its receive window, it does have that same sequence number here. So receiver does not know that whether it is the first 0 or the second 0. It simply sees that yes, it is 0, so it will simply accept the packet with that sequence number. Okay, so that's why it is happening. As I said, that the receiver does not know what's happening at the sender side. Okay, so the receiver's behavior is identical in both the examples. In one of them, in the first one, as we saw, that everything is fine because whatever packet was being sent was the actual packet that the sender was actually trying to send. Okay, that means the sequence, even though the sequence numbers were the same, that means packet 0, they were being received in the correct order. But in the second example, we saw that because the receiver does not know anything about what's going on at the sender's side, it considers that whatever packet it is receiving is actually the one that that it is expecting, but originally it is not the case. Okay, so that's what a problem, I mean, that's a problem in case of selective repeat protocol. Okay, so what is needed in such case? Okay, so we need a relationship between the sequence number size and the window size. Okay, that means how much the window size should be and what should be the sequence numbers, so that we can avoid such a problem to happen. So this is basically a very big question, and a lot of research is being going on this, that what should be the ideal sequence number and what should be the ideal window size. All right, so the answer for this is actually in the book. It is a well researched answer, but it is still there is some research going on in this one to have that ideal value, but there is some value that is already given in the book. So I would like you to just go ahead and read this answer in the book. Okay, that is what should be or what is in general assumed, that what is the relationship between the sequence number side and the window size of this selective repeat protocol. Okay, so please go ahead and take a look at it. All right, so now we are going to move to TCP. We have already studied a lot about reliable data transfer, and now we are going to see one actual protocol that talks about or that guarantees reliable data transfer. Okay, so that is basically TCP in case of transport layer. So it is known as a connection oriented protocol. Okay, so these are the RFCs corresponding to TCP. Okay, as has been given here, these are the RFC documents. They have all the information related to how TCP should work in a particular scenario. Now, the as of the future, features of TCP, what we know is that it is basically it provides point-to-point communication. We do have one sender and one receiver. It follows a client-server architecture, and it provides reliability. And of course, in order delivery also is provided. There are no message boundaries as such. It allows full duplex communication. That means bidirectional data flow is allowed in the same connection. We have something known as the maximum segment size. Okay, So this is we are going to look at it in the next slides, okay, during some of the concepts used in TCP. Okay, the maximum segment size that can be transferred over the medium. All right, it's known as the MSS. We do have cumulative acknowledgements in case of TCP. Then pipelining is also used. Okay, so it is used and so that we can actually have congestion and flow control in TCP. Now we do have corresponding window size to allow congestion control and flow control. It is of course a connection oriented architecture, so that means there will be a handshake that will happen before communication happens between any two entities. All right. Then it is of course a flow controlled protocol. So the sender should not be able to overwhelm the receiver with sending large number of packets. So let's check out the TCP segment structure. This is the one. So it is basically, the header is basically 32 bits. We do have the source port number, the destination port number. We have sequence number, which is nothing but the segment sequence number. Now, it is how do we find out what is the segment sequence number? So to make it easier, what we do is we just find out that what is the sequence number of the byte that is being sent. Okay, so the first byte in the sequence, that becomes the segment sequence number. Okay, so this is basically kept so that we can count the number of bytes of data into the byte stream. Okay, not the sequence, I mean segment. Okay, we are not counting the segment here, we are basically counting the bytes of data that are there in the byte stream. Okay, then we have the acknowledgement number, which is nothing but the sequence number of the next expected byte. Okay, so this A is basically, this is what is going to give the A bit. So this is the acknowledgement. All right. And then of course we have the data that is sent from the application layer side into the TCP socket. So few more variables or few more information that are there in the TCP segment. This is the checksum value. We do have some options. We will see what these options are about in TCP. Then we have the length of the header for TCP. Then we have flag bits, 3 flag bits, RST, reset, sign flag, and finish flag. Okay, so that those are for connection management. We are establishing a connection before transmitting the packet, right? So these are the flags that are used for establishing a connection. We will also see how this connection establishment happens. We do have a receive window. This is for flow control. Okay, that means what is the number of bytes that the receiver is willing to accept. Then we have a few more flag bits here known as C and E, which are used to give congestion notification. That means whether the medium is getting congested or not with a large number of packets. That information, for exchanging that information, these bits are considered. And we do have the data pointer, URG data pointer. Okay, so that is always not used. Now let's see the TCP sequence numbers and the corresponding acknowledgements. Okay, so see, we have the window size of n here. These are the ones, the green ones, which are basically sent and acknowledged. These are the ones, the yellow ones, which have been sent but they are not yet acknowledged. The blue ones have not yet been sent but they are in the window, so they can be sent. And then the rest of them are there which are not in this window size, but as and when the window slides, they will get into the window and they can be sent later on probably. Okay, so what are the sequence number? Okay, so as I mentioned, it is the byte stream number of the first byte in the segment's data. Okay. So if this packet or basically this segment has to be sent from the sender side, what is the information that will be sent? Of course, source port number, destination port number, and then you have the sequence number. Okay, so from the sender side, you are sending the corresponding sequence number, and these are the other options that are there in the header. Now you will fill them according to how, what you are basically sending. Now, at the receiver side, we will be dealing with the acknowledgement numbers, right? So at the receiver side also, let us assume that, this is the same window size. Now, the previous ones would be, the green ones would be the ones which are acknowledged, and the yellow ones are basically, these are the ones for whom the acknowledgement is still not received, right? And so on and so forth. Now, what the outgoing segment of the receiver would do once it receives a packet, it will simply see this is the acknowledgement number and the corresponding flag bit, that is A, in case of you just saw in the previous slide. So these two values will be changed and the corresponding segment will be uh, transmitted over the medium. Okay. Also, we have the concept of cumulative acknowledgements here. That means a number of acknowledgements, if they are received continuously or cumulatively, then what to do. Okay, so that also we need to take care of. Okay. Now, before that, if the receiver handles out of order segments, then how do we handle this kind of a scenario? Okay. So now TCP specification does not actually specify that what should be done if the receiver handles out of order segment. Okay. So it depends on the whoever is implementing the TCP, the TCP receiver or sender side. So according to the implementation, either they can be buffered or they can be discarded depending upon what kind of protocol you are using. Okay, so as such, the TCP specification does not say about what will be done if the packets are received out of order. Now, this is a simple telnet scenario, that is both host A and host B will be communicating with each other. So, so at the communication, when somebody is requesting some data, so in that case, there will be a client server kind of a connection. Okay, so TCP sequence numbers we will see here, and we will see that how acknowledgements are also numbered here. So suppose the user types C, okay, so that information has to be sent back to B. So the segment number that is being sent is, please remember that the sequence number that we are talking about is basically the byte stream number of the first byte of data that is being sent. Okay, so sequence number 42, and because it is an exchange of data that's happening, so it is also sending an acknowledgement of some data that was sent by host B. Okay, so acknowledgement number here is 79 and the data that is being sent from host A side is C. So now it is, when it is received at host B side, the host acknowledges this receipt of C and echoes back that it has received C. How does it do that? It simply sends, what sequence number it actually is, you know. So this is sequence number 79 that it is basically sending out, and it is sending the acknowledgement for 43. By that, what it is meaning, that I have received what data you have sent to me. Okay. Now I want the next data. So the next data in sequence would be 43, because this was the one that was sent from the sender side. The host A had sent sequence number 42. So the next one in sequence should be 43. So what the host does, that it simply says that I have received sequence 42 and this is what I'm expecting. So that's what it sends in the acknowledgement number. Okay, so that is ACK equals to 43 here. Similarly, if you see in the previous one, the acknowledgement given was 79 from host A's side. That means host A is expecting data with byte stream number 79. Okay, so that's what host B is sending with this. It is sending data with sequence number 79 and it is acknowledging the acceptance of or receipt of the data with sequence number 42 here. Now, once this data is received at the host A, what it will do, it will acknowledgement the receipt of echoed data, that is C, that is this one. So it basically sends the next data in sequence, that is sequence number 43, and acknowledges also the receipt of data of sequence number 79 and asks for the next data in sequence, that is 80. Okay, so this is a simple telnet scenario of how the TCP sequence numbers and acknowledgement numbers are basically working with each other. Okay, so this is please take a look at this. Sometimes students make they make mistakes in writing the sequence number and acknowledgement numbers. So just go ahead and take a look at it once again so that you have the concept very clear with you. All right, I have already mentioned this part. Okay. Now, next question is that how to set this timeout value. What is this timeout value? When you are sending a packet, you do have a timer. Once the timer goes off, that means once the timeout value is reached, then the sender will resend the packet, right? But how to decide what should be the timeout value? So when we had studied about this in the previous classes, we had seen that this timeout value is somehow calculated. We had not seen how to calculate it. So today we are going to look at that how the timeout value is calculated in TCP. Okay, so what should be the features for finding this timeout value? Okay, so one is that the timeout value should be longer than the round trip time. Of course, otherwise it will always tell that there's a timeout and it will always resend the packets, right? So it should be longer than the round trip time, but the round trip time can vary because of all the issues that can happen while transmission in the network, right? Because the network can sometimes be congested, it can sometimes be free, right? So the RTT always varies. So that is one challenge. Then the next is that if we have too short of a timeout, then of course, as I mentioned, that if the timeout is too short, then you can have premature timeout, which will lead to unnecessary retransmissions. If the timeout is too long, then basically you are having a slow reaction in this, right? So whenever there is a segment loss, you are waiting too much before you can retransmit the segment again. Okay, so these are basically the challenges to actually find out that what should be the ideal timeout value in case of TCP. So how should we estimate this round trip time? Okay, so this is measured using this sample RTT value, which is nothing but measured time from segment transmission until acknowledgement of receipt. Okay, we are not considering the retransmissions here, just transmitting a packet and then getting the corresponding acknowledgement without any retransmissions in between. So now sample RTT can vary. Okay, so what we want the estimated RTT to be a bit more a smoother value. Okay, so that you can actually keep it for all the next or subsequent transmissions that will happen. Okay, so whenever such things happen, that means whenever things a lot of data is there and they're all random values, what we do, we get the expected value. Okay, so the same thing is going to be done in case of sample RTT also. Okay, now let us see how it works out. So we estimate the RTT using this, that is estimated RTT equals to 1 minus alpha of estimated RTT plus alpha of sample RTT. Okay, so this is nothing but you are, so this equation is nothing but you are basically taking the value from what has happened in the past. Okay, so here you are basically averaging out with a set of data that you are seeing in that has happened in the past. You just average out and then get the estimated value of the RTT that should be there in case of TCP. Okay, this is known as the exponential weighted moving average, or EWMA. Okay, so it is, as I said, that it is the influence of past sample and it decreases exponentially fast. Okay, so the alpha value is taken as 0.125. Okay, so this is the RTT value in case of, RTT values and the time graph. Okay, so the blue ones represent the sample RTT value and the pink ones represent the estimated RTT values. Okay, so as you can see that, the sample values vary a lot. Okay, they can vary a lot, but this estimated value is more or less giving a average value of it. Okay, so this is how it actually gives us the estimated RTT value. Now, once you get the estimated RTT value, your job is exactly not done yet. Okay, you can estimate the round trip time, but then you need to have some safety margin or time also with that. Okay, just to have the timeout interval. Okay, so the timeout interval is nothing but the estimated RTT plus some safety margin. Okay, so now there can be a large variation in estimated RTT values. So the safety margin, if one can argue, then the safety margin should also have a larger, it should also be a larger value, right? Now, if you see that if you have a large safety margin, then also you are making your timeout a lot bigger than what it should be. So there also we have a challenge as to what should be the safety margin. Now, what do we find? How do we find out what should be the safety margin? By finding out the standard deviation in the estimated RTT values and then multiplying it with 4. Okay. So the timeout interval is nothing but the estimated RTT value plus 4 times the safety margin. Okay. That is the standard deviation in the RTT values. Okay. Alright. So this is how your deviation RTT is basically calculated. That is 1 minus beta of dev RTT plus beta times mod of sample RTT minus estimated RTT. And the beta value is given as 0.25. So this is also an EWMA. That is, this is also an EWMA of, that is the estimated weight of the sample RTT values, as we have calculated similarly the estimated RTT value. So with this we are getting the dev RTT values and the beta value taken here is 0.25. So now let's see what happens at the sender side. Okay, so once data is received from the application, what is done? The corresponding segment should be created for transmission. Now in the segment, as we know that each segment should have its corresponding sequence number, which is nothing but the byte stream number of the first data byte in the segment. Okay, now if you are transmitting the segment, of course the corresponding timer has to be started. Okay, so if the start, so that is why it is given here that start timer if it is not already running. Okay, so now think of the timer as for oldest unacknowledged segment. Okay, what's the expiration interval? It is known as the timeout interval. Now suppose the event that has happened is that there is a timeout. Okay, so what the sender will do? It will retransmit the segment that actually caused that particular timeout and it will restart the timer again for that particular segment. Now suppose the event is that the corresponding acknowledgement is received. So then the acknowledgement, so if the received acknowledgement, the packet that has been ACK packet that has been received, it acknowledges previously unacknowledged segments. Then what is done at the sender side, it updates what has been received as the ACK packet, right? That means if it has received the acknowledgement for packet number 0, then it will simply update that this packet has been received and acknowledgement has been received for this packet also. And if there are still unacknowledged segments, then it will start the timer. So this is a tabular format of what happens, of the events that happen at the receiver side in TCP. Okay, so this is the event that is happening at the receiver side. That means arrival of in order segment with expected sequence number, and all data up to expected sequence number are already acknowledged, right? That means you are expecting sequence number 2, the receiver is expecting sequence number 2, and it already has sequence number 0 and sequence number 1. It already has received them. Okay, so that means it is in sequence, and it is also in order. Sorry, it is in sequence and it is a correct packet. Okay. So then what should be the action that the receiver will take? Okay. So now if suppose there is a delayed acknowledgement, so in that case, what the TCP receiver would do, it would wait up to 500 millisecond for next segment. If there is no next segment, then it will send the acknowledgement. Now next event, if the arrival of in order segment is there with expected sequence number, but one other segment has its a pending acknowledgement. Okay, so in that case, so we have a TCP receiver action. What is it? Immediately send single cumulative acknowledgement and send acknowledgement for both the in order segments. If there is an arrival, so the event at the receiver is that there is an arrival of out of order segment, and it is basically a higher than expected sequence number. Okay, so there is a gap that is detected between what was expected and what has been received at the receiver side. The TCP receiver action is that it will immediately send duplicate acknowledgements indicating sequence number of next expected byte. At the receiver side, the event is that there's an arrival of segment which is partially or that partially or completely fills the gap between what has been expected and what has arrived at the receiver side. Okay, so there's a difference in the sequences. So what the receiver's action should be, a TCP receiver's action should be that immediately send acknowledgement, provided that the segment starts at the lower end of the gap. Okay. Now let's check these example scenarios. These will clarify most of the things. So yes, so sequence number 92 is being sent. Now this is 8 bytes of data, right? So what we know, sequence number of a segment is the byte stream number of the first byte of the data that is being sent, right? So this is the sequence number 92. The size of the data is 8 bytes. Okay, so what will be the and what is the receiver doing when it is sending an acknowledgement? As the acknowledgement number in the acknowledgement packet, it will send again the sequence number of the first byte of data that it is expecting. Okay, so it will it will just simply send in the acknowledgement what is the next byte of data that it is expecting. So if the sequence number is 92 and it is of 8 bytes, so the acknowledgement number would be 100 from the host side. So unfortunately, the acknowledgement could not reach the host. There was a timeout that occurred. So once the timeout occurred, so then again the packet was resent at the host, and the host, once it received it correctly, it simply sent the acknowledgement again. Okay, so this is the lost acknowledgement scenario. Now let's see another retransmission scenario. So we have the sequence number equals to 92. This is the base, the pointer send base is at 92 here. Okay, so this sequence number is sent, and there's a it is an 8 bytes of data. So then the next sequence number that will be sent from the host A side. So we are having more than one packet transmission here. So that is the sequence number is 100. Now it is a 20 bytes of data. So the corresponding acknowledgement numbers that will be sent from host B side would be 100 and 120, of course. So once 100 is received, the send base value will again change to 100. And once the next acknowledgement is received, which is of 120, then the send base value will change to 120 also. Okay. Now, suppose there is a premature timeout. Okay. That means before these acknowledgements could be received, there was a timeout that occurred. Okay. Now, suppose now let us see if this timeout has occurred here. So then what would happen? It will simply send cumulative acknowledgement for sender for packet 120. Okay, so it will send the acknowledgement as 120. So that means once this acknowledgement is received at the sender side, I mean at host A side with send base 120, and again there's one more acknowledgement for the same packet. Okay, so these are the cumulative acknowledgements that are received at the host A side. Now, next is this one. Now, suppose there is a missed acknowledgement in between, but the next acknowledgement is received. Okay, so then what would happen? See, once the acknowledgement with the next sequence number is received at the host, then the host will simply get to know that, okay, fine, that up to 120 has been received. It will simply assume that up to 120 has been received. It will not think of the one that was sent, that is sequence number 100. So it will simply send the next packet in the sequence, that is with sequence number 120, and it is having 15 bytes of data. So that is why it is given here that cumulative acknowledgement covers for earlier lost acknowledgement. So even though they see, remember, acknowledgement will be sent from the receiver side if only it receives the corresponding packet. So if the sender is receiving a higher acknowledgement packet, so that means it is basically assuming that all the packets before that have actually been received at the receiver side. So that is why it is not going to bother for this acknowledgement of packet number 100 here. All right, I think, yeah, I think it's already, yeah, 2:55. Okay, fine. So I will stop the class here, but I do have some announcements and all for the class today. So first thing is, as you all know, that, this time